Friends, today we will discuss about the synchronous machine representation. Now, so far we have developed the synchronous machine model considering the rotor circuit and stator circuit resistances and inductances. Now, with this stator circuit and resistor circuit, rotor circuit inductances, the complete model of the synchronous machine is developed. Now, however, there is one practical problem, that the various inductances which are used actually in modeling the synchronous machine are in general not available or cannot be measured directly from the certain standard tests, and the parameters that is the inductances and resistances of the stator and rotor circuits are which are used in modeling, right, have been called fundamental parameters or basic parameters. Now, the standard the practical practice is now to use derived parameters which can be measured by performing tests at the terminals of the synchronous machine. Now, these derived parameters are very important and the machine data are given in terms of the derived parameters. Okay. Therefore, today we will try to relate the derived parameters with the fundamental parameters of the synchronous machine. Now, to understand this concept of derived parameters, let us first look at the direct axis network of the synchronous generator. Let us say that this black box represents the direct axis network, and we have two pairs of terminals shown here. This pair of terminals represent the stator side of the synchronous generator. This pair of terminals represents the rotor side of the synchronous generator. That is, at these terminals we inject the field voltage, okay, and at these terminals the stator circuit current is coming out. Okay. Now, we will be representing this machine by two networks, one direct axis, another quadrature axis, right. Now, in the direct axis network, the direct axis current is the output from this network, and we are looking for what is the flux linkage in the direct axis due to this particular excitation at the field winding and the load which is supplied by the synchronous generator terminals. Now, here the convention is that we have used the synchronous generator convention, where the terminals the currents are leaving the stator terminals, that is the generator convention. Now, with the generator convention, the direct axis current is leaving the terminal of the D axis network. Okay. This network, this diagram represents the Q axis network. In this Q axis network, we represents the current leaving the network as IQ, and at the terminals we look for the quadrature axis flux linkage psi q. Now, here in these two diagrams which I have shown here, instead of showing the current ID, flux linkage psi d and applied voltage EFD, we will be representing this in terms of small perturbation. So, that input quantities shown are delta EFD and the output quantities shown here as delta ID and delta psi d. Similar is the situation in the q axis network. Now, here we will be representing the mathematical model relating the flux linkage delta psi d. Now, when we develop this model, we will be developing first the model in terms of what we call as operational parameters. Operational parameters, that is, we will represent delta psi d as equal to minus L d s into I d s plus a transfer function we will call it G s delta E f d s. This is a very standard way to start with, that is, we are trying to relate the current, flux linkage and the voltage applied to the terminals of the synchronous at the field winding of the synchronous generator in terms of what we call as the operational parameters, that is, this LDS is the operational direct axis inductance. Operational, we understand what is the meaning of operational here, right, but this parameter S which I have shown here, the S is the familiar Laplace transform operator. Now, if you recollect actually the circuit theory, then in circuit theory we represent the operational impedance of a RL circuit as R plus S L, is not. This is the operational impedance, we can call it ZS. That the same approach is used here. Now, our problem basically will be to obtain an expression for LDS and GS in terms of fundamental parameters, or we call it the basic parameters of the synchronous generator. Now, this equation I have written here, because when I consider the small perturbations, the same equation is written here, okay, minus LDS into delta IDS plus GS into delta EFDS, okay, plus IDS. Now, similarly, we can write an expression for quadrature axis network, the delta psi qs equal to minus LQS delta IQS, because in the case of quadrature circuit there is no applied voltage and there is no a field circuit on the q axis. Okay. On the q axis we have always the damper circuits. Now, in this expression, this transfer function Gs is the stator to field transfer function. Stator to field transfer function, you can easily see here that Gs, suppose delta ID is 0, that is machine is under no load condition, okay, then you can easily see that delta psi ds will be equal to Gs times delta EFDS. Therefore, this transfer function relates the stator to field transfer function. LDS is the direct axis operational inductance, okay. LQS is the quadrature axis operational inductance, okay. Now, our interest here is now to develop a relationship between the operational inductances and this transfer function Gs with the fundamental circuit parameters, of the synchronous generator. Now, for doing this we again start with our basic equations of the synchronous generator. Okay. Now, in this case of synchronous generator, we had developed the flux linkage equations. These flux linkage equations now are written in the operational form, that is psi ds can be written as minus L d I ds. The current is now operational current, L A d I f d s plus L A d I 1 d s. Now, here while writing the equations, I am considering one damper on the direct axis, right. Therefore, we were denoting the damper winding by the symbol K d. K used to stand for the number associated with the damper winding. Therefore, since K is 1 in this case, it becomes L 1 d. Further, we are assuming that the all mutual inductances are same, so that this L A d appears in both the terms. Okay. Similarly, we write down the flux linkage for psi f d s as minus L A d I d s plus L A d I 1 d s plus L f f d I f d s, right, and the flux linkage of the damper winding in the operational form is written here. Now, these three equations were derived earlier, and what we have simply done is that we have now put in the operational form. Okay. Similarly, the EFDS when it is written, that is the field winding voltage, right. We are writing now expression for EFDS in operational form again. Now, when you write this expression for the operational form, EFDS, when you write the equation, right, then it comes out to be S times psi f d s minus psi f d 0 plus R f d I f d s. That is, you take again the standard equation for the field circuit, right, because in the case of field circuit we have the term d by dt of psi f d. E f d has a term d by dt of psi f d, and therefore, when you take the derivative, and that when you take the Laplace transform of the derivative, you will have the initial condition that will appear here, because in the previous equation these were the algebraic equations. Now, equation for E f d, it has a derivative term, and therefore, this appears. Similarly, actually we write down an equation for the damper winding. There is no applied voltage, right, but still we have d by dt of psi 1 d. Therefore, again you will find that initial. Therefore, now what we do is that in order to avoid the initial values, we express these equations in terms of incremental values, okay, so that under steady state conditions the incremental values are 0. Okay. Therefore, when you use these incremental values, the equation will have straight away the form delta E f d s equal to S times delta psi f d s plus R f d I f d s. This is a very important equation. This is very straightforward actually. If you look in terms of our basic equation, right, then we have applied voltage is equal to R I plus L d I by dt. Okay. Therefore, you can write out R I plus d psi by dt. Okay. This is what we have already derived. Now, in this expression you substitute the expression for delta psi f d s. Okay. Delta psi f d s we have already written earlier, that is use this expression for this delta psi f d, and here they are all constants. You can convert this delta ID, delta I1D, delta IFD. Okay. And you substitute the expression for delta psi FD as here in this expression and then simplify. When you simplify this, this delta EFD will appear as minus S times delta LAD, delta IDS plus RFD plus S times LFFD, delta IFDS plus S times LAD, delta I1DS. That is, we have written now incremental field voltage, right, in terms of the 3 currents. Okay. Similarly, write down this expression for damper winding also, because in the case of damper winding the applied voltage is 0, right. Therefore, you have this is minus S LAD delta IDS plus S LAD delta IFDS plus R1 plus S L11D delta I1DS. Now, at this stage again let me reiterate actually that we want to relate the stator circuit quantities to the rotor circuit quantities, right, in terms of the stator variables and rotor applied field voltage. That is the expression which I have if you look at this expression, delta psi ds is equal to GS delta EFDS minus LDS delta IDS. In this expression or in the second expression, the rotor currents do not appear. Rotor circuit currents, that is I1D or IFD, these 2 currents do not appear. Therefore, what we do is that we eliminate these currents. From this, using these equations, what we do is that you eliminate these currents. Now, to eliminate this, what you do is that you use these equations and write the expression for delta IFDS and delta I1DS in terms of delta EFD and delta ID. That is, these 2 equations associated with the other equations which are derived earlier. Right. What we do is that we write the expression for delta IFDS and delta I1DS in terms of this quantity and these known quantities. That is, we are trying to eliminate the field current and the damper circuit current. Now, this step is little what involved step, but you can obtain it. Once you obtain this expression, next step will be to substitute this in the expression for delta psi ds. Whereas, if you look actually the expression for delta psi ds, delta psi d, this is the equation for delta psi d, equation. Equation for psi d is here. In this equation we have ID, IFD and I1D. Okay. What we have now done is that IFD is this will be expressed in incremental form. Then once you express in incremental form, in this expression you replace this delta IFDS and delta I1DS using those expressions. Once you express, you will find that you can write the expression for delta psi ds as GS delta EFDS minus LD IDS. Do you appreciate this these steps? Now, once you do this thing, what will happen is that this expression for GS which you get will be written as, that is 2 expressions, LDS and GS. The LDS will be written as LD multiplied by an expression of this form 1 plus T4 plus T5 into S plus T4 T6 S square divided by 1 plus T1 plus T2 S plus T1 T3 S square. That is, when you do this simplification and express delta psi ds in terms of delta EFDS and delta IDS, right, then the coefficient of delta EFD term will come out to be in this form, that is GO equal to GS equal to GO into 1 plus SKD divided by 1 plus T1 plus T2 S T1 3 S square, while the expression for LD will come out to be equal to this. The yes. Then these constants which are shown in this equation are related to the fundamental parameters of the synchronous generator by this expression, that is GO equal to LAD by RFD, TKD is LFD by R1D, T1 equal to LFFD by RFD, T2 equal to L11D by R1D, T3 1 upon R1D multiplied by L1D plus LAD LFD divided by LAD plus LFD, T4 1 upon RFD LFD plus LAD into LL divided by LAD plus LL, and T5 as 1 upon R1D multiplied by L1D plus LAD L1 LL divided by LAD plus LL, and similarly T6. You can easily see that when you perform this simplification, right, you will be in a position to express the LDS, they express this GS as a ratio of two polynomials, right. The denominator here is of the second order and the numerator is one order less than the denominator. Similarly, LDS is expressed as ratio of two polynomials where the order is same. Further, the denominator of LDS and GS are same. This denominator for LDS is same as that of the, okay. These derivations can be carried out. Now, at this stage what is done is we write the expression for LDS, that is the operational direct axis inductance, as LD multiplied by numerator, that is by this expression, which is having numerator as 1 plus S times T D prime into 1 plus S times T double prime, 1 plus S times T D O prime plus into 1 plus S times T D O double prime. That is what we do is now this operational inductance will express in terms of time constants, and these time constants, as we will see, are the standard parameters of the synchronous generator. Because these are the parameters that is going to determine the transient performance of the system. Okay. Similarly, since GS has the same denominator, right, therefore, when you put in this form here, GS can be written as 1 plus S times T D O prime S times T D double prime. Okay. Now, our interest is that we know the expression for this time constant T1 to T6 in terms of basic circuit parameters. These are all known. We want to relate these standard parameters, that is this time constant T D O prime, T D O double prime, T D prime, T D double prime, to our basic parameters or fundamental parameters. Now, to correlate this, before I correlate, I will just write one more expression, that if we follow the same approach as we have done for d axis, we can write the expression for LQS as, that is operational quadrature axis inductance as LQ multiplied by 1 plus S times TQ prime into 1 plus S times TQ double prime divided by 1 plus S times TQ O prime 1 plus S times TQ double prime. Now, again these constants TQ prime, TQ double prime, TQ prime, TQ double prime, these 4 time constants, right, are again the standard parameters of the synchronous generator. Right. Now, to obtain an expression for these parameters in terms of T1 to T6, what we have to do is that we compare this denominator and numerator terms. After all, actually we had written earlier, let us say LDS. LDS is written in this form. See, this LDS is written as LD multiplied by this expression, okay, and LDS we are now writing in the form of, in this form in terms of these time constants, okay, while these are our standard parameters, and as we will see that they can be measured from the certain tests which can be conducted at the test on the synchronous generator. Right. Now, at this stage we see here actually this expression, look at this expression. First I will just look at the denominator, 1 plus T1 plus T2 S plus T1 T3 S square. Now, in case suppose you have instead of T2 here as T3, then this can be broken into fractions. You know, suppose actually you have the expression of this form, 1 plus T1 plus T3 into S plus T1 T3 S square. The partial you can find out the factors of this expression. The factors will be 1 plus T1 S into 1 plus T3 S. Okay. Now, if it is in this form, then directly you can identify that T1 is equal to TDO prime and T3 equal to TDO double prime. But incidentally, the expression is here 1 plus T1 plus T2 S plus T1 T3 S square. Now, here we make use of one simplification, an approximation we can say. The approximation is that in practice R1D is very large as compared to RFD. R1D, which is the resistance of the damper winding on the D axis or amortiguer on the D axis, is very large as compared to the field winding resistance. When you make this assumption, T3 and T2 and T3 come out to be very small as compared to T1, and T5 and T6 will come out to be very small as compared to T4. Right. Therefore, in the expression for the expression which we have is, in the denominator we have 1 plus T1 plus T2. Therefore, this T2 is negligible as compared to T1. Okay. Now, T3 is also very small as compared to T1. Therefore, first step, suppose I neglect T2, I will not create much error. Second actually step is that suppose I add T3 to this term, then also I am not going to create big error. Therefore, what we do is that this denominator, which is actually 1 plus T1 plus T2 into S plus T1 T3 S square, right, will be replaced by this term 1 plus T1 plus T3 S plus T1 T3 S square. The justification I have just now told you that T2 is very small as compared to T1, Similarly, T 3 is also very small as compared to T 1, right. Therefore, what we do is that we neglect T 2, but we add T 3. We do not create much error, but we simplify our Richardson expressions. With this, you can see here 1 plus s time T do prime becomes 1 plus s time T do double prime, which is of course the standard. And when you make these assumptions, I have just told you the approximation, not assumptions, approximations, then you can write down this you can equate the two denominators and you get this type of expressions. In the case of numerator, the approximation is that T 5 and T 6 are very small as compared to T 4, right. Therefore, we are now getting a simple expression of this form. Remember that when I am making this assumption that T 3 is very small as compared to T 1, right. In the product term T 1 T 3 s square I am not making any approximation, T 1 T 3 remain there. Now, when you do this, you will find actually that T do prime can be identified as T 1, T do double prime can be identified as T 3, T d prime can be identified as T 4 and T d double prime can be identified as T 6. While we know that T 1 is equal to L f f d divided by R f d. Similarly, T d double prime is equal to 1 upon R 1 d multiplied by this expression, and expression for T d, T 4 and T 6 were also derived. Therefore, they are all time constants. You can easily see that this term T 1 is equal to ratio of inductance to resistance. Therefore, it has the characteristic of a time constant. Okay. Here also in this bracket you have inductance term divided by resistance, therefore, this also is a time constant, right. And now we are relating actually these two time constants, that is the we call actually the standard time constants, right, are related to the basic parameters of the synchronous generator. We will see actually that this time constant can be measured by performing tests. Okay. Now, at this stage let me just sum up what we have done till now is that we have started with the operational model for D axis and Q axis windings of the synchronous generator, okay, and then using the standard equations, okay, for the synchronous generator stator winding and field winding, right. We have established the transfer functions for GS and LD and similarly for LQ. Then assuming that this can be expressed in terms of some time constants or the standard parameters, we have established actually that this time constant can be related to the basic parameters. Okay. Now, till now actually my whole discussion I have not talked about what is the tangent reactance, what is the tangent inductance, what is the subtangent reactance, subtangent inductance. But we all know actually that whenever there are sudden changes in the synchronous machine operation, let us say a fault, okay, then the currents are induced in the rotor circuits and these currents will decay at certain rate, and the rate of decay of these currents are determined by the time constants. There are certain time constants which determine the rate of decay of the currents. I just take the case that whenever there is a short circuit, currents will be induced in the damper windings, they will be induced in the field winding, right. Similarly, in the damper winding of the Q axis and so on, and they decay with certain time constants. Okay. Now, first we will try to establish that what will be the inductances offered by the synchronous machine when sudden changes take place or the tangents take place. Now, to understand this, what we do is we start with, let us look at this expression for LDS. This is the expression for LDS. Okay. Now, suppose I want to know the behavior of the machine under sustained disturbance condition, that is the when the machine is carrying the steady state currents. At that time I can substitute S equal to 0, S equal to 0. When I substitute S equal to 0, then this LDS will become equal to LD. That is, this operational inductance for S equal to 0 will become LD. That is, LD is your synchronous direct axis synchronous inductance, because at that time the currents are under steady state conditions, this sustained conditions. Therefore, now I can say that under steady state conditions S is 0, and therefore, LDO, that is the operational impedance for S equal to 0, is same as the synchronous inductance or D axis synchronous inductance. Now, you consider another case, let us say S is approaching infinity, a very high frequency tangent. When S approaches infinity, it means actually the tangent is of short duration, right. Then the frequency associated will be very large. If you make this situation, that is the rapid transient condition, then this LD double prime, we will represent this operational impedance for S equal to infinity as LD double prime, right, and this will come out to be equal to LD multiplied by this expression. Now, what we are trying to say is that the inductance offered by the direct axis under rapid tangents is denoted as subtangent inductance, and this subtangent inductance is related to the synchronous inductance by this expression, these time constants. Further, if you assume actually that there is no damper winding in the circuit, let us say that there is no damper winding in the circuit direct axis, only there is a field winding, right. Now, at that time when there is a rapid tangent, right, the inductance is denoted as LD prime, and again S is approaching infinity, right. This will come out to be equal to LD into TD prime upon TDO prime. Therefore, now I can say here that we have identified the three different type of reactances offered by the synchronous machine, that is synchronous inductance, subtangent inductance LD double prime and tangent inductance LD, starting from the operational inductance point of view. And the expressions for this, if you just look into the complete expression, because when you substitute here the expression for TD prime TDO prime, okay, in terms of the fundamental parameters, you will get the full expression for LD double prime, okay. And these are expressed in terms of the basic parameters. The expressions are quite lengthy, you can write it down. Similar exercise can be performed for Q axis, that is, you can perform the same exercise for Q axis, and you will find actually that the time constants are TQ prime equal to this and TQ double prime equal to this, again expressed in terms of fundamental circuit parameters. Right, and this tangent and subtangent inductances of the quadrature axis winding, damper winding, and the parameters are also given. Now, we have to just look slightly in more detail about these time constants. Now, here if suppose I perform a test on the synchronous generator with stator terminals open, that is under no load condition. When we perform a test, right, where we consider the synchronous terminals open, then this term will absent, this term will be absent. Under this case actually we have relation with the field direct axis field flux linkages, direct axis linkages with respect to delta EFDS. Therefore, this transfer function GS affects the change in d axis flux linkages as the change in the applied voltage of the in the field circuit, okay. And this change is determined by the two time constants. One time constant is TDO prime, another is TDO double prime. Now, since this test is performed under open circuit condition, okay, therefore, this time constant TDO prime is called direct axis open circuit time constant, or we always call the open circuit direct axis time constant TDO prime, okay. And the TDO double prime is called the open circuit subtangent direct axis time constant. Here actually the TDO prime is called, basically full name is it is open circuit direct axis transient time constant. The transient word is also there, TDO prime, okay. And this time constant is very important actually when you model our system. In fact, one can perform one test, very simple test actually on the synchronous generator, and that is normally called the steady state frequency response, not steady state, what you can call another term is stand still frequency response test. In the stand still frequency response test, what is done is that you keep the machine stationary, not rotating, okay. You apply field voltage and vary the frequency of the applied voltage, okay, and measure the output voltage of the machine, and plot actually the phase, plot the gain versus, that is the applied voltage at the field winding and the output voltage at the terminal of the synchronous generator for a range of frequency, right. Once you make this plot, and then this plot can be, that is this curve can be fitted with the characteristic of this GS. You can do the curve fitting, right, and by doing the curve fitting you can identify the time constant TDO prime and TDO double prime and TKD also, right. Now, over the years in the literature actually lot of emphasis has been laid down on measuring the synchronous machine standard parameters. Therefore, when I talk about standard parameters, the standard parameters are the synchronous inductance, subtangent inductance, transient inductance, then these time constants, right. Now, these are parameters called as the standard parameters, and these parameters can be measured by performing tests at the synchronous machine terminals, and lot of work has been going on actually to measure accurately these standard parameters of the synchronous generator, particularly those who are actually working in the field actually, right. Sometimes you will come across where you have to measure these parameters by performing the standard tests, and lot of literature is available on performing these tests. Even IEEE has given some standard tests to be conducted for measuring these standard parameters. Now, in the case of salient pole machine, there is one small additional point to be learned, and it is something like this. In the case of salient pole machine, we provide the damper winding in the face of the pole. The pole is a laminated pole, while actually if you talk the round rotor machine, the rotor is a solid, it is not laminated one, right. And therefore, you can always identify or you can represent actually cottage axis by two windings, two damper windings, right. While in the case of salient pole machine, there is one damper winding provided, there is only one damper winding. Now, once there is only one damper winding, you cannot have any distinction between the tangent and subtangent inductances. LD prime and LQ prime and LQ double prime, this distinction is not possible, they are same, okay. And therefore, this for salient pole machine, we subtangent and tangent they are same. There is tangent, there is no mention of tangent, we always call up subtangent, okay, because we are considering the damper winding, one damper winding only. These are the expressions for salient pole machine. Further, you will see actually in the literature actually, or this discussion will show you that these are the relationship between the different type of reactances, because when you talk in per unit system, the inductance is same as the reactance, okay. These are the standard relations which are given. Now, I will just quickly tell you one more point actually before I close my discussion here, that when we started the study of tangent stability, I talked about the classical model, and in the classical model I said that the synchronous generator can be represented by a constant voltage behind tangent reactance, and this representation is valid when we assume the field flux linkage psi FD constant. If you assume this psi FD constant, right, then the voltage behind tangent reactance or direct axis tangent reactance becomes constant, okay. Now, this we will quickly derive actually and show you that yes, how it happens. Now, the steps involved are like this: you write down the per unit flux linkage in the d axis, psi AD, you can just write down psi AD is equal to minus LAD ID plus LAD IFD. Here we are assuming the mutual inductance is same, okay. Psi D is equal to psi AD minus L1 ID, okay. This is the difference between psi AD and psi D. Psi FD is psi AD plus LFD IFD. These equations are standard, we all know it about it. Now, using this last expression, what we do is that we find out the expression for IFD. We find the expression for IFD. The IFD comes out to be equal to psi FD minus psi AD upon LFD. We eliminate the term IFD from the first equation, that is psi AD which is equal to minus LAD ID plus LAD IFD. You substitute the expression for IFD. Then psi AD will be written in the form minus LAD ID plus LAD upon IFD, psi FD minus psi AD, okay. When you rearrange the whole thing, you rearrange the term that is psi AD, you take it out on this side and express psi AD in terms of other parameters, it will come out to be equal to psi AD is equal to LAD prime into this term, where LAD prime is defined like this, okay. Similarly, for psi AQ, one can write down the psi AQ as equal to LQ prime minus A. Now, here we will make one more small assumption here, that the tangent saliency we will neglect. We will assume that x d prime is same as x q prime, right. With this assumption, now we can write down our d axis voltage E d equal to R A I d minus omega psi q, which is written in terms of psi A q, I d and I q. This is E d. That is, in this expression for E d, you replace this psi A q. Now, once you replace the psi A q, E d can be written in terms of I d, I q and E d prime. That is, this expression for E d is written as minus R A I d plus x d prime into I q plus E d prime. This E d prime is the important term here, which is expressed here as E d prime equal to minus omega L A q prime into this. If we assume this psi 1 q constant, that is the flux linkage in the q circuit also constant, right, then this term is a constant term. Similarly, when you can write down for E q, where it will be written in this form minus R A I d I q minus x d prime into I d plus E q prime, where this E q prime is written here as omega L A d prime into psi f d upon L f d. Okay. Therefore, this E q prime is written in terms of psi f d and E d prime is written in terms of psi a d. Therefore, this E q prime and E d prime, if you assume these two fluxes to be constant, they will remain constant, right. Once these two voltages are constant, I have established here that this voltage E prime, that is the voltage E prime, that is the voltage behind transient reactance, can be written as E d prime plus j times E q prime. And when these two voltages are constant, this E prime is also constant. Now, here you have to look like this, that is, suppose I consider that this is my q axis, okay. This will become d axis. Let us say this is our E prime. This quantity is going to be E q prime, this is going to be your E d. Now, if E q prime is constant, E d prime is constant, E prime is constant. If suppose these are our q axis, let us say that the reference axis is shown somewhere here, this is R and I, these are our reference axes, and we measure the angle with respect to the reference axis, that is E prime. This angle is measured as delta. Now, you can easily see here actually that so far this E prime is concerned, right, the magnitude of E prime is constant and its position with respect to q axis is fixed, right, and therefore, for studying the stability I can measure the angle of E prime with respect to some arbitrary reference, it may be synchronous rotating reference frame or so on. Therefore, here you will find actually that the component of E prime, call it say E r, and E I, this is actually I and R, they will be varying as the delta varies. Therefore, there are two important points to sum up here. One is that this E prime remains constant when you make this assumption. Second point is that position of this E prime with respect to q axis is fixed, and therefore, I can measure the angle with respect to angle between E prime and any reference frame for performing my stability studies, right. Let me sum up here that today we have developed the relations between the standard synchronous machine parameters with respect to the basic parameters, and also we have established that the classical model, in the classical model if you assume this flux linkage is constant, then the voltage behind transient reactance is constant, right. Thank you.